welcome Ed Bauer.
Thank you. Thank you. Before I get started on this, I just want to mention that it's 54 years past, and in trying to gather information for this, I basically had the two journals that we published, and all the photos that I'd taken in the past on this were gone. I don't know where they went. So everything I've got on here is pretty much taken out of the two journals. So if some of it isn't as bright and beautiful, that's why. So anyhow, Tom Rudolph is all, I've included him here because Tom was project leader. He and I are about the only two left in the area that worked on this. There's several others that are still alive and around, but mostly it was just him and me. He's not here because of age and health at this time. What happened? Okay, I hit it too hard, I guess. Anyhow, Tom was the first editor on the pre-irradiation journal. And for permanent staff on that project, Tom was project leader, and then we had two ecologists, a biologist, three of us were technicians, health physicists to do all the dosimetry work and detection of radiation, and then we had a secretary. That was our staff at the time. These are the two journals. That's just a top half of the books. The one on the left is the pre-irradiation journal publication that talks about what we thought would happen. It also, and for the first part of this, it'll cover a lot of the setup and everything that went into it. And then the back one here is the post-irradiation journal. The Enterprise Radiation Forest Project was initiated by the Atomic Energy Commission, which is now the NRC, the Nuclear Regulatory Commission, and the U.S. Forest Service. In 1967 is when they first started talking about it. And the criterion that were required by our people, Nienstedt, McShee, Stearns, and Rudolph, were primarily, one was existing, we had existing field, gamma field already and lab studies on radiation for response of trees to it. The area selected had to be within 30 miles of the lab. Contiguous block of large land, the remote area away from human habitation, flora and fauna. Flora and fauna typical of a northern forest community, topography devoid of any real extremes, you know, hills, valleys, and land ownership had to be public. So those were the criterion, and the reason we did it is the AEC approached the Forest Service primarily because we had ongoing research in that area, but they wanted to study what the impact of radiation would be on an entire ecosystem in the event of a nuclear disaster, whether it would have been, you know, with Russia or whatever, or from a nuclear plant. This is what we had for existing facilities. The one on the left is the Institute of Forest Genetics, is what it was called then. Later it was called the Forestry Sciences Lab, and now it's Institute of some, I forget what it is now. But it's another institute now. And the gamma field was west of the laboratory, and the next slide here shows how the trees were planted in concentric arcs away from it, so doses would be the same going across. I worked on this. This was my primary area of responsibility when I came on board in 1967. It was put in 1965. The description of the area and stuff is by the three people up on top. You can see a map here. Rhinelander's right up there in the center, and down there the big square area is where I think there's a pointer here, isn't there? Nope. Oh dear. Oh, here it is. No. Anyhow, the square area is where the radiation source area would be, and this is kind of a blown up area. The area across the bottom is a highway, but the rest of it is all county lands. So you can see all the sections surrounding it without any habitation or anything else. And the radiation site itself was 1,440 acres. The entire area was fenced with anti-personnel fencing, which was 8 foot high with 2 strands of barbed wire and a V across the top, and of course posted with caution radiation signs every 100 feet. What I'm trying to convey here is that none of this was taken lightly by any means, and regulations from the Atomic Energy Commission commanded that we do all this. That was the control building, and that was on the east side of the area. If you look at the area going back here, it would have been at the far lower right-hand side. You can see the dark circles as the building, and the treatment site was on the opposite side. This was the stand area. The base of the mechanism with the arrow going to it is called a lead pig. That's what they ship them in. So the container, instead of building a separate unit, the field area that I showed you, the unit was 6 feet below ground in an oil bath. This one here, we didn't have the luxury of doing any of that because we're in the middle of a forest setting. And so this one here, we used the lead pig. The top of the lead pig is a solid lead piece that's 6 inches thick, and then the stainless steel tube containing the radioactive material is attached or welded onto that. And so what happens is you have the stainless steel tube that goes above that. The source would be raised to the top of that for irradiation purposes, and the cables and everything had to be buried in the ground because the radiation solidifies the coating on the cables. And the motor drive was, electrical, I forget what you call a magnetic device. So if a power failure came into place, it would slowly lower the source back into the container. The pipes that you saw that coming down, we used those. They're steel pipes that we used for shielding in the event of a tree falling or something on that line. The source, and you could see there, the stand was very heavy timbers, buried deeply and cemented into the ground. And then the motor guide tube, the whole thing was bolted solidly to the base of that. All of that to ensure that if we had storm or wind or something, it didn't pick it up and carry it away. The source itself is a 10,000 curie source of cesium-137, and the irradiation cycle was 20 hours a day. This gives you an idea of the relationship of gamma radiation to light waves and everything else. The thing to remember about this is that there was an article done in the Sentinel Journal a couple of years ago by a young lady. She came and interviewed Tom and myself, and I kind of got the feeling that she thought there was residual radiation in the area and wanted to do the article. Point I'm making is gamma radiation is like X-ray. It's in that stainless steel tube. It's a very powerful radiation, but it won't be anywhere once it's in that shielded position. And like the field unit we had, once once we dropped it below ground into that oil bath, there's no radiation. You can work right next to them, and you're not getting irradiated. The shielding on this one was that lead pig. So gamma's way on the outside over there, 10 to the minus 12, and your visible light's way up there at 10 to the minus, what, 3, 6? Radiation containment. It's, like I said, contained in that stainless steel tube attached to the lead pig lid. The source is raised and lowered by a motor and cable mechanism. Power failures would lower the source into the pig. Gamma radiation is like X-ray, it's what I just explained. And there's no residual particles. When that thing's taken away, which is what it did in the end, there's nothing. There's absolutely zero radiation anywhere. And the source originally came from Puerto Rico at the rainforest down there. They reloaded it, brought it up to us, and I don't know where it went after that. It went back to Brookhaven Laboratories. Radiation safety equipment that we had, I believe, if I remember right, 3 Victorine survey instruments. And when I'm talking about survey instruments, we had them where they read very low level radiation and also up to somewhere around like close to 1,000 R. Pocket dosimeter, everybody was required to carry a pocket dosimeter, a film badge. We had audible chirpers as well. And then the source itself, when it was in a down position in that blockhouse or the control building, we had a control unit that had 10 keys in it. And when you went in, you took a key out, put it in your pocket, and that unit would not work unless all 10 keys were in and turned on. That was the safety precaution. Quarterly leak tests were done on all of this equipment, whether it was at the unit by the lab or this one. And that meant, like for the one out in the field where the oil was below ground, we had to pump the oil every quarter because it would solidify from the radiation if you didn't. And so we use the oil, we'd send in a sample to them for testing. Film badges were always tested. And the pocket dosimeters are immediate readout. So you would set them to 0, go into the area, and when you got back, you take a look and read them. Whoops. There we go. And obviously, because this was a forest setting that was just logging roads, basically, we needed some specialized equipment to get to the area. We had one 4-wheel drive truck with a power winch, and believe me, we used it on quite a few occasions. 2 half-ton trucks, a sedan, and we had one very large snowmobile. And back in that time, you know, snowmobiles were pretty rough shape. I mean, they weren't smooth riding like they are now. And the one we had was a big Polaris that had a reverse in it. It weighed 600 pounds. You didn't want to get it stuck, trust me. We had a Cushman Trackster, and that was really our workhorse. It did just about everything we wanted in this setting. Before we did any radiation work or anything, we live trapped all the deer using DNR, the old wooden DNR traps, and they were very heavy. Put them on a trailer and sled them around with that Cushman scooter. The Polaris wouldn't pull them. So, like I say on the bottom, the road conditions really sucked. This is a map just showing how it was laid out. There's one small lake in there. And this was the treatment area, and the control site was down at the far bottom left. And those are the transects that ran, like the one running up that way was a white birch. The other one coming down is northern hardwood white birch. The one going that way is a mixture of that and aspen. And just to show you the thoroughness of what we did, all the trees were individually labeled. So that gives you an idea of every tree and where it was in that treatment area. We also labeled shrubs as well. And for herbaceous species, we did a 1 meter plot along those transects. And I forget what the exact distances were, but I think it was like at, I believe it was like a 10 meter, 30, 50, and 100 or something like that. This just gives you an idea of the contour of the area. You can see the lake, and up on top is where one of the roads came in for access that we had to punch through the forest to get there. And that's within 50 meters of where the source sat, so you can see that the contour is really pretty level in everything, and that was what we were really striving for. That's a forest type map showing the different forest types, whether it's aspen, maple, birch, whatever. And I know you can't read them, I can't either. This is soil types. And so you can, and again, you can't see the numbers, but it gives you a list of what the soil types were. You had corduroy peat and loam, Goodman silt loams, and so on. And out of the 2 volumes, we had, this is the list of the authors that were on them, and there are 33 manuscripts with 13 authors. And so what I tried to do, instead of doing every manuscript separately, which would have been very long and laborious, I tried to clump them a little bit and recognize the appropriate authors for each one. The first thing that we had to do is get a list of all the flora and fauna in the area, and we were pretty fortunate. One of our scientists, his wife, Joanna Clausen, had her doctorate in botany, and so she came out and identified all the plant species. And so we wound up with 52 families and 193 species in the area. Dosimetry was done by Brad, who is our health physicist, and it was used, the way we did it is using lithium fluoride. And lithium fluoride salt, when you anneal it before you expose it. In other words, you put it into under very high temp, and I'll get into that later. But anyhow, the lithium fluoride, we had both the powder in little plastic capsules, and then also some Teflon-coated discs that had lithium fluoride embedded in them. And then we developed standard curves with a 260 Curie source. It was a portable irradiator in my office that we would use direct read ionization chambers, so we could tell exactly what the dose was at a given increment of time. And so we would take these and set them in, develop standard curves, and then everything was read based on those standard curves. That's Brad's radiation scale for a 20-hour day, and pretty hard to read, but close in or right next to it would have probably been about around maybe 15 to 2,000 R per day, per 20-hour day. And then as you get further away, it's the inverse square law. Double the distance, you have or quarter the value, if I remember right. Come on back. Let me go back here. make sure this thing keeps jumping around. Okay. Okay, for dosimeter placement, what Brad did is, because we had those 1 meter plots, we also used them as a place to measure dosimetry. So he took bamboo stakes, put them in the ground, and then you'd have one at the base, right on the ground. You'd have one up at 3/10 of a meter, and then at a meter. And then for the trees, we had monofilament line on a pulley device, so you could raise and lower them on that. And so he had them at 1.536 meters, and then 9 to 12 feet using the pulley system. And then they were also placed on the front and the back side of the trees, because trees attenuate greatly on the radiation. And here you can see on the ground, you can see one packet, you can see it up there, and then at the very top. And that's how he did those. And then that's for the tree itself. Here's where I was jumping ahead of myself a little bit. To zero out the lithium fluoride, you heat it to 400 degrees C in a muffle furnace. And then after exposure, you reheat it in a Victorine. We used a Victorine 2800 reader, and it records the luminescent readings. What will happen is lithium fluoride under that heat will luminesce, and that's how you develop the curves. You just measure the known values and get your curve off of that. And the discs also were extremely accurate. All of that is a very, very accurate system. Let me look here. To predict the radiation effects, we look at ICV, which is interface chromosome volume. And what that is it's a measure of the nucleus and the number of chromosomes, and you divide the number of chromosomes into the nuclear volume, and that gives you the ICV value. And the ICV value in radiosensitivity is, if the larger the nucleus and the smaller the number of chromosomes, the more radiosensitive the plant is, or humans, or whoever. And so in order to do that, Joanna and I went out. I collected 3 apical buds from all the species. We did about 79 of them. And I killed and fixed the samples using a Craft 3 solution, embedded them in Paraplast and sectioned all of it, and then photographed them and measured them using an actual millimeter device on the photograph. And to predict, like I said, that's the way you predict them. So sensitivity is related to the nuclear volume and the chromosome number. And for a reference, humans and animals, it takes about 640 R to kill you. That's acute exposure. And I mean, that's immediate exposure. Trees are much, much more tolerant, and so are other plant species and et cetera. Tree species, so, withstand probably in the neighborhood of 1,000 R or whatever in that light. There's the relationship, and I know you can't read it, but at the very top is Abies balsamiae, in other words, balsam fir, being the most sensitive, and the ICV value on that one is 31.46. And if you get down further to one of the maples, and you can see it's like 3.08 for sugar maple. So it gives you a range of how that works. And let's see. This is based on that ICV grouping. We gave a prediction on what would happen at the various rates. And the furthest one over is 1,500, I believe, R per day. And everything that we predicted would just be killed, it'd be gone. From 300 to 1,500, lichens survive. And between 250 and 500, you're into the grasses and that type of thing. And when you get down to the trees, angiosperms are at like 30 to 65 R per day. So it gives you a real broad range of where you're at. Temperature and moisture regimes, that's just a chart showing from 70 to 73. And you can see in 72 and 73 very little difference between any temperature and moisture. We had a major weather station in an open area closer to the control unit where we did all the rainfall and snow melt and everything. And then within the plot, we had the individual stations. Here you can see that rainfall was way too variable to make anything out of it. It just was all over the place. And again here, stress from temperature and humidity isn't evident in 72 and 73, the two bottom ones. Vapor pressure did show a difference from 72 and 73. It was 3.4 for a control and 4.5 on the irradiated end of it. Light distribution. And in 72, there's no difference, and that's the irradiation year. So you have to remember that's when everything got irradiated. So between the pre-treatment and 72, there's really not much difference in light or canopy change. And then in September, within 0 to 30 meters, and you can see it on the bottom one here, you can see how it's splitting out from the, like the 20 R per day, it's starting to split out. 71 is down below 72 is up much higher. So you're getting much more light, and it increased from, in September at 0 to 30, it increased from 5 to 64%. And in 73 and 74, it went at 0 to 50 meters, increased by 80 to 800%. And you can see it there. At 71 and 72 is your irradiation period, and you can see they're almost identical. And then you look at 73 and 74. So what has happened is it's killed off the vegetative leaves and stuff on the trees close to the source. And so you get this tremendous increase of light. And we had a colleague at Michigan Tech that did the study on lichens for us. And they exhibit very high resistance to radiation. The damage appeared only at distances less than 7 meters from the source. So that shows you just how much they can resist. Part of it is because cell division on lichens is extremely, extremely slow. I mean, it takes years for the cells to divide. So, they're very inactive in that sense. That's a picture of the lichen on the tree. And the damage that he observed was the lifting and breakage of the lobes. And you can see 2001 and 2002 are the two trees. But what you get is you get a side view of how they were lifted, because he talked about that. There's a browning of the pigment and the slowing down of the thallus growth, which is the part that comes out. And that's a microscopic end, and it shows the damage to the thalli. The area on the left has been irradiated. The one on the right is your control, so you can see how it's blowing the thalli apart. And then effective gamma radiation on the ground vegetation. And you don't see it as good in the charts, so I've got a table over there that explains it more. The biomass of the ground vegetation in 71 for aspen was 93.2, and the maple, aspen, birch was 42. 72 for the aspen went from 93 to 79. It's not a real dramatic drop, but you look at 73 and you're way down. So you're seeing that the biomass that falls into litter traps and stuff on the ground is way down. So what we have is death of the trees, and so you're not getting as much litter drop out of the trees in those years. Floral changes in the understory, approximately 90 species of understory plants. And in 72, biomass at 1,000 R per day was greater was sharply reduced, and few plants survived. In 73, they were significantly reduced at 300 R or greater. And in 73 to 74, at 73 and 14 to 40 R per day, there was no damage, virtually nothing. Gamma radiation in total. Okay, this is for the herbaceous cover in the maple birch area. And if you look at the very bottom line, that's 73, 72 on the far left. That's the highest dose rates. So you can see that it's way down. There's virtually no biomass on 73 at that bottom part. So the trees have died and you have no litter production there. Okay, now we're getting into the shrubs here. That's Tom Crow did that. Woody seedlings, shrubs, and saplings. The low shrubs are plants that are 30 to 100 centimeters, and the tall shrubs were 100 centimeters or 25 millimeters in diameter. That's the type of litter traps we use to collect any leaf fall, whatever comes out of the trees. You have a screen in the bottom, and then the top is also a screen, so you pull out the bigger material on top, and then the seed and stuff gets trapped at the fine bottom screen. Damage to the arboreal structure, and if you look at the 1972, woody seedling damage was restricted to 1,500 R per day or greater. Low shrubs were dead at 500. High shrubs were dead at 500 or greater, and saplings dead at 500 or greater, and the herbs showed very little damage at that level. And the reason that herbs don't really show a lot of damage, and this came about when I did the collection for doing the nuclear volumes. A lot of your herbaceous plant material, the growing tip is below ground. So you've got attenuation by soil and everything else that prevents them from getting as highly damaged. In 73, almost all the seedlings were dead at 500 or greater. Cover and biomass at 100 was greatly reduced. Cover and biomass in the high shrubs was reduced at 40. So you can see the low shrubs are better at adapting to it than the high shrubs. And your herbs at that point were recovering totally in 73. And then in 74, there was recovery on the low shrubs and on the high shrubs. looking at radial growth, which was a very good way of determining what's happening to trees, and that's looking at the cambial growth in a tree. And to do that, I inserted stainless steel pins in this whole procedure was done by a person at the Forest Products Lab, I believe, if I remember right, Carl Walter, in 1968. And he inserted stainless steel pins, and what it does is when you stick them in through the cambium, it produces a damaged parenchyma cell. And so in successive pin insertions, you can go down. What I did is I had to kill and fix the material and section it all, and then put it under a scope. I stained it. The parenchyma came up totally different in color because I used, differential staining techniques. And so I could easily measure from the previous week to the next week to the next week on how much the cambium grew. And I used ocular micrometers on a microscope to do it. So radial growth chart for balsam and red maple. And what you can see is the clear block is the 1970, I believe, 1970 collection, and that's pre-radiation. And then you have 72 on the front and the back side of the tree. And so for balsam fir, if you're over at the far left, which is your highest radiation in a given treatment, you can see that front and back are gone. They didn't grow. You look at maple, the front side didn't grow, but the back side did some. And then you get into the next dose level, and you can already see, like on balsam, it's still severely depressed from the pre-radiation. In the maple, it's nowhere near as bad, and then it just keeps coming out more and more normal. So you can, from that, you can also see the attenuation effect of the wood. These are the observed phenology of the gamma-irradiated plants. Herbaceous, 1972, the year of irradiation. Herbaceous plants, no real sign of damage. Early senescence at rates of 300 or greater. In 73, delayed shoot elongation by weeks or months. And in 1974, they're all back to normal. The woody plants and seedlings, etc., tall and low shrubs, dead at rates of 100 R or greater for a day. Total shrub biomass was 500 R, is reduced by 70 to 80%. And then in 73, almost all seedlings were dead at 500 or greater, and no change under 100 R. And then for biomass, it was reduced for low shrubs at 100 R and tall at 40. So you can see again that the difference between your tall and low shrubs, the low shrubs are more resistant because they can withstand a much higher level of radiation. Low shrub recovery in 74 was at 1,500 and tall at 500. Trees, premature leaf colorization and radial growth showed the most damage, which we just went through on the radial growth. In 73, you had delayed leaf out, and all balsam fir were dead from 25 meters in, and maples were dead at 240. And in 1974, you had a normalization of trees showing good recovery, normal leaf flush, and more normal growth. So you can see they're recovering pretty fast. Shoot elongation, as it was affected. If you look, the top one is balsam fir. And you can see the dark black line that basically showed they were pretty much dead at that point. This is distance from the source on the right-hand side, so it's much lower. That's the beginning distance over there, or the furthest away. And so you can see the drop as you keep getting closer to the source on the different species. An overview of the phenology: the herbs show very little damage during a radiation year and recover quickly in the following years. And part of that could also be because the canopy is more open, so they're getting more sunlight and everything else as well. More rain, there's less competition. Seedlings and shrubs, radiosensitivity understory appeared to be size dependent. In other words, woody seedlings are more resistant than low shrubs, and low shrubs more resistant than saplings. And for the trees, they show very little damage during the irradiation year, and in the following years, damage and recovery follow the IBC principle. And yeah, we looked at small mammals too. And basically, the trap system was one that was done by Iverson and Turner. So the trap sets in the middle, that's just a trap shelter, the wooden part, because we had to shelter them. Interesting byline on that is in winter of 70 and 71, we had 52 inches of snow on the ground. Well, when you're snowshoeing out there and you have to get down to a trap that's at ground level, we had a couple of guys, and myself almost included, where we're on our head in there and can't get out because you got snowshoes on and no tree to grab onto and all that stuff. So it was interesting. The mammal species go from the masked shrew up there and white-footed deer mice, and you get down to black bear and all that. Those are the mammals that were there at the site. This is just a grid showing the trapping, and we trapped for a 5-day period in a month. You go out the first day, put your trap, and then each sequential day you pick up the trap, and on Friday you empty them out, put them away. The traps were baited with apples and peanut butter. The grid, you saw that up there. The animals were ear tagged and toe clipped for identification. Paramuscuous is the white-footed deer mouse. The eastern chipmunk and red squirrel were the three most accessible data for all of this, so we ignored the other ones in the data collection. During the irradiation year, lithium fluoride dosimeters were attached to the ears on these guys. And with the exception of a very few, most of them stayed. It was those little Teflon discs. And it's amazing. I would have thought they'd have probably come off or pulled out or something, but they didn't. Dosimetry range and trapping cycle, this is during the year of irradiation. Cycle 1, the accumulated dose was like 0.1 to 610 R. Cycle 2, which was in June, was 0.7 to 1180. And in cycle 3, it was 0.2 to 740. Not totally sure why that shift was there. There were some weather conditions in July that, we had quite a few storms and stuff, and they might not have moved around this much. What was it there? Okay. The estimated total exposure for each species: the white-footed deer mouse, 1,218 to 1,220 R. Chipmunk was 610 to 2,300 R, and red squirrels was considerably lower. My guess is that it's because the red squirrel is up in the tree more. and so going to be further away from the source. So my guess the accumulation wouldn't be as high there. Chipmunks, because they're all over everywhere all the time, my guess is the reason that's why they're showing much higher level. And then again, you look at the white-footed deer mouse, and their path is under leaves and debris on the ground, and so that would be my guess on that. And you can see here that the last capture date shows most of your animals are over at that almost control area of no radiation. And then you've got a few outliers that show up, you know, but you don't know. It might have been a new animal that came into the area and was still able to get around even in a high radiation area. But almost starts making one think that they can detect radiation. I don't know. That'd be another whole study. And this is a chart of basically saying what we predicted and what actually happened. So for the, for the completely devastated zone, we had predicted no vegetation, and yet there was vegetation in there. You know, the lichens and a lot of the herbs, ground herbs were there. The next one on the lichens, we had figured it, you know, they'd be pretty much gone, but wound up being there. And for the angiosperms, essentially the forest, the original forest, except for conifers, would be okay, and that was about the way everything was. What actually happened was what we had predicted pretty much on those. On the radiosensitivity, the lichens were about 250 times more resistant to the radiation than northern deciduous forests. And tropical forests are about 20 times more resistant to radiation than northern forests. And my guess is because of the water. Water is a tremendous attenuator. And so you're getting, you know, 200 plus inches in a tropical forest versus, you know, 20 inches here. And so your plants are going to contain a lot more water within them. And that's my own personal feeling about why they're so much more resistant to radiation than our natural forests here. And that's it. Question? Two.
My two.
Yeah.
I don't know where Chernobyl occurred in relation to your studies, but did that event generate any communication within the science community? And two, the individual who, from Milwaukee Journal-Sentinel, and you and I talked about that, I sent an email there with a copy of the article they wrote, it was like 2 years ago.
Yeah, yeah.
And they didn't get any response. When that person came to develop that article, they must have had some sort of bent or prompt to come to you and say, let's tell this story. And do you have a sense of what that was and what they accomplished or not, or what your
Okay.
your communication was for those two issues?
As to your first question about Chernobyl and was there any contact scientifically back and forth, I don't know if they ever contacted anybody like in our State Department or anything. I know that this would have been helpful to them because it could have saved them a lot of time and effort in going back. Now, it's different in the sense because there you have particulate radiation. It's not gamma. So you've got all this particulate material laying out there, and so I don't know how these two would actually dovetail together because there you've got animals dragging it around or wind blowing it. So it's a whole different situation. As to the reason for the interview from the Sentinel Journal, when we were talking to her, Tom and I both kind of got the impression that she thought there was something that was still in the area, you know, radiation-wise. Yeah, that she thought that somebody, I think, had talked to her and probably told her there's some residual stuff, which there isn't. Yes?
Is it possible to get any information? I mean, do you have a publication of this study?
Yeah, those 2 volumes that I put the slide up with are the only 2 publications on this. And I I know that Madison, the library down there, has copies of them.
Okay.
Other than that, I really don't know. I have my own 2 personal copies. And I mean, if you wanted to ever look at them, you're more than welcome to.
Are they online at all?
No.
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 And I have another question.
Yes.
What was the name of the lake in the Enterprise Township?
Has no lake, no name.
Oh, no name.
It's a no-name lake. It's a little bog lake. I think it's only like 3 acres or maybe 4 acres.
Okay. And I have heard that, or read somewhere, that radioactive materials are stored for many years in the river bottoms and lake bottoms. A study done of the silt material.
Mm-hmm. Yeah, there are radioactive particles in the soil. I mean, uranium's in the
that's
soil
true.
and all that stuff. So you're gonna, as the stratum goes down and water tables wash things away, you'll probably expose things like uranium and whatever other compounds are in there that are radioactive. Fortunately, in most cases, they're probably very low level radioactive materials. See, and the reason we use cesium versus cobalt, cobalt's a much higher energy wave than cesium, but the half-life on cobalt is only 9 years, and in cesium it's 33 and a half. And when I'm talking half-life, that means all radioactive materials decay, but they don't decay in a straight line, they decay in an exponential manner. And to reach half the value, that's the 33 and a half years for cesium and 9 years for cobalt.
Does that ever affect compasses?
No, I don't think so. And just for another one, carbon-14 half-life is 1,440 years. So, you know, some of these compounds, and I'm sure there's stuff like carbon-14 and some of that too. But any other questions? Yes.
You dismantle all your test equipment when you were through with this.
We kept some of it, the real low-level survey instruments. We kept those because we still had some check sources and other things. See, for all of this, the irradiator we had an X-ray machine and then the 2 field units. And for testing your instruments, we had what they called check sources. So they were small sources in a container, lead container. And you could take and read a reading off them every day so you knew your instrument was working. Okay, and later on, when there was no further study, they put them on excess property. Yes?
For you and Jim, there was discussion of some radiation research on.
Oh, yeah, I was,
Whatever came of that issue?
Well, I had asked Tanya this morning about that, and she didn't have a whole lot to say. Maybe, she said to ask for Ryan, and I didn't think of asking him when he was here. So he's gone, so I can maybe bring that up with him tomorrow.
yeah,
But I've been asking them for the information, because I remember years ago when we found this radiation cooker, we called it, that they painted and burned wooden boards with low-level radiation just to see how it drifted through the air. Plus, then I also found those newspaper articles in the Monroe County newspaper from 1961 or 2, that they spread irradiated sand on some of the trails on Fort McCoy, or put it on the roads in the cantonment to do some sort of testing. I can't remember what it was. But yeah, I don't know if you probably didn't have any.
We
To
had no link to any of that.
Okay.
We had no knowledge that they were doing it.
So yeah, it's something I think it's interesting, and it's something to delve into more, some of this Cold War era stuff that, you know, once it became 50 years old, it became
Yeah.
historical, and so then probably get money to start studying it more.
Yeah, see, and that was why we started ours too, because of the AEC. So,
One last one.
yeah,
Review again the genesis of the whole issue, you know, Atomic Energy Commission, who set the stage of, let's set this up? Where was the idea that we should do this?
it came from the Atomic Energy Commission to do this study. The study, the work that we were doing with the gamma field prior to that, and the irradiator, in-house irradiator and stuff, was to study genetic variability, and also to try and identify different chimeras and that kind of thing, genetic markers. And so that was why they had gotten into it in that sense. But then because we had already a fair amount of equipment and had been under, you know, both USDA radiological safety and also the AEC, you know, it was logical that they brought it to us.
This was focused on northern or boreal forest, and there was something in the tropics as well?
Yeah, the source we got was from the Institute of Tropical Forestry in Puerto Rico. So they were doing yeah, they had that same source down there, doing the same thing.
Any other places?
They had one, they've done it at Oak Ridge Laboratories in Tennessee, and I believe they had one out in California or somewhere.
Okay, so different forest
Yep,
settings.
it was, from what I know, it was Forest Service looking at, you know, ecological studies in a natural setting.
That pretty much brings us to the end of the
Okay.
time, so thank you, Ed.
You bet. Thank you.